Now let us make you understand what are confounders. Supposing there are intercondylar fractures, about 100 of them, and 50 were treated conservatively and 50 were treated operatively. Now 40 out of 50 in the conservative group did better and only 30 out of 50 in the operative group did better. So naturally your next next patient you will treat conservative. But supposing we add this information that conservatively treated were undisplaced fractures and operatively treated were displaced fractures, then the displacement of the fracture becomes the other explanation of why the conservative group did better. And this displaced undisplaced factor, which can alter your perception of the comparison between conservative and operative treatment, is called as confounder. Now let us try to understand these confounders and how to control them better. So here we are treating intercondylar fracture, the lower end of the humerus, and the controversy is whether we should treat them conservatively or operatively. Now, if somebody does a retrospective follow-up of conservatively and operatively treated groups and says that 50 out of 70 in the conservative group did better, did good, and only 10 out of 30 in the operative group did good. So for the next case of intercondylar fracture, your choice will automatically become conservative. Now let us add some new information to this and then see whether your choice changes or not. Supposing we found out that 70% of the conservatively treated were undisplaced fractures and only 60% of the operatively treated were displaced. So the displaced, the fact that the fracture was displaced may be an explanation of why operative group did worst in this case. So this displaced or undisplaced fracture is the other explanation of the difference in the result of treatment that we see, and therefore this other explanation is called as confounder. So this is the confounder. After this, let us see how to control this confounding. So the first method of controlling confounding is restriction. Supposing we restricted the conservative and operative treatment groups only to undisplaced fractures, then obviously the confounder status is fixed to undisplaced only. This is called as restriction. But it's a bad method because we would not be able to tell what happened with the displaced fractures. So this is restriction. The second way is that for each undisplaced fracture in the conservative group, you have one undisplaced in the operative group, and for each displaced fracture you have one here. So on the confounder status, that means displaced versus undisplaced ratio, both conservative and operative groups will be similar, and therefore the displacement would not be able to create a difference in results. So this is called as matching. Then the third thing that we can do is that we can analyze the relation between good and bad results and conservative and operative treatment in the undisplaced fractures separately and in the displaced fractures separately. So there are two strata, undisplaced fractures where we have made a 2 by 2 table associating conservative and operative treatment to good and bad results. And there is another table, 2 by 2 table for the displaced fractures. And then if the uh, risk ratio or measures of association like risk ratio or odds ratio are sufficiently similar in the two strata, then we can combine the results of the two strata to give an adjusted odds ratio or adjusted risk ratio, adjusted for the confounder, the undisplaced versus displaced strata. So here is the overall table which will give us the crude relative risk and the crude odds ratio. See, this is conservative or operative treatment. This is good or bad results. And 50 out of 70 cases is the risk of, is the chance of a good result. 50 upon 70 is the chance of a good result given the conservative treatment. And 10 out of 30 is the chance of a good result given the operative treatment. And the odds are 50 upon 20. The odds are 50 upon 20. And therefore, odds, the denominator 20 does not contain the numerator 50. In the risk, it does. So this is the risk in the conservative group. This is the risk and the odds in the operative group. And 50 upon 70 divided by 10 upon 30 is the crude relative risk. And 50 upon 20 divided by 10 upon 20 is the crude odds ratio, associating conservative and operative treatment to good and bad result, unmindful of whether the fractures were displaced or not. Now we split this table into the displaced fracture table and undisplaced fracture table, and here you will have an adjust. If we can combine this odds ratio and risk ratio and this odds ratio and risk ratio, we will have a common association between conservative and operative treatment and the good and bad result, keeping the confounder displaced or undisplaced constant. Because in these tables, this table is only for displaced fractures. So this table, the confounder is irrelevant. And since this table is only for undisplaced fractures, therefore in this also the confounder is irrelevant. And if we can combine these two odds ratios and risk ratios, that will be adjusted for confounding. This is called as stratified analysis, separate table for different strata of the confounder. So we'll show you how the stratified analysis works in the next slide. Now let us show you how to do this stratified analysis. We'll use the same numbers, and what you have to do, you have to go to the stat calc, and in the stat calc you have to actually go to 2 by 2 table, and here you feed the numbers of one strata and second strata. So we are talking of the first strata, and the numbers there were 25, 5 and 10, 5. Then we take the second strata. Here is the second strata, and we feed the numbers 30, 10, and 5, 5. So it is giving me the uh, odds and risks parameters of strata 1 and strata 2, but it is also combining the two tables, the two strata, and it's giving me the risk ratio, and it's the crude and the adjusted odds ratios for the and their 95% confidence intervals when we combine the displaced and undisplaced tables. So if you want to know what happened to the displaced table, this is it, and this is the result. If you want to see strata 1, this is the result. And if you want the summary, that means combination of the both, then this is the risk ratio of 1.3095 upper and lower 95% confidence intervals. So using the StatCat table, you can actually combine the displaced, the undisplaced, and all the strata of the confounders. But if there are multiple confounders, then the numbers in these cells become zero and stratified analysis cannot be properly done. Then you resort to regression analysis to control the confounders. So in regression analysis, here is your good or bad outcome. It is equal to, so this is the determined variable, and these are the various determinants. So there will be some constant number which these variables have been unable to explain, plus B1 into treatment type, beta 1 into treatment type, plus beta 2 into confounder 1, and 2, 3, 4, 5, 6, right up to beta n up to confounder n. So here, this beta 1 value will tell you the relation between treatment type and good and bad outcome, keeping all confounders C1 to Cn constant. So this regression analysis is able to deal with multiple confounders, and the exponential of this beta 1 is actually the odds ratio. So we'll show you this regression analysis in the next slide. However, if this outcome is numeric, for example, how much was the diastolic blood pressure reduced? So if it is numeric, then the method of regression used is linear regression. If the outcome is binomial, for example, here the good and the bad result, so that then we use logistic regression. And if the outcome is time dependent as to when did the patient die, patient of cancer treated by treatment A or B, when did they die? So that is time dependent variable. Then you use the Cox proportionate hazard model. And all these three options are available in EpiInfo. So supposing there are multiple confounders, and not only the treatment type but the displacement of the fracture, whether it is simple or compound, what was the duration of the fracture, what is the age of the patient, all these things, whether it is right hand, left hand. So there can be many other explanations of whether you will have good or bad results of treatment. So let us see how to control them. Control all these confounders so that whatever is the difference between conservative and operative treatment is only explainable by the treatment type. So we make a file like this. Here are your case numbers from 1 to 20. Now here are the results, good or bad, and here is the treatment type, and these are the possible confounders C1, C2, C3, C4. You see that some of these confounders are 1, 2, 3, that means ordinal variables. Some of them are 0, 1, that means either present or absence, which are called as categorical variables. Some are numeric. So all these confounders will control so that you can get the relation between good bad results and the treatment. So these are the two columns, this one and this one, which we are trying to associate, keeping C1 to C4 constant. Let's see how to do it. So we open our EpiInfo. We go to Classic. We say read, and we say that the data is not one of the recent ones, but it is an XLS file. Then we say browse, and when we say browse, we go to the desktop and we say that this is regression to control confounding, this file. Say open, say the first, this is the first row contains header information, then sheet 1 has the data, and we say OK. So it has read these records, and we want to find out whether the results were good or bad. So we use logistic regression, and we say good or bad results is the outcome measure, and we put all other variables like C1, C2, C3, C3 and C4 as the other explanatory variables to the treatment type, and then we finally place the treatment type. And when we do this, we find that this result, this odds ratio 0.3395, this odds ratio is adjusted odds ratio for all the variables C1, C2, C3, C4, all have been adjusted, and now this treatment good or bad result, this is the association keeping the treatment and good bad results. So this is the method of regression. Again, treatment type, this is the odds ratio of treatment type adjusted for confounders C1 to C4. This is how you use regression analysis in controlling confounding. So stratified analysis or regression analysis can deal with only known confounders. The only way to deal with known and unknown confounders is to randomly allocate to the treatment groups over a sufficient sample size. Now we teach you here how to do random allocation. So we open the Excel file. We go to the blank workbook. We say that here are your case numbers, say 1, and in the second column we say equal to sum bracket open and say 1 plus 1, which makes 2, and then we Control C, copy this, and whatever is the number of cases that have to be randomly allocated, let us say they are 30, and we say Control V, and so these are the 30 ID numbers that we want to randomly allocate. Now we say there are 2 treatment types. Let us say 3 treatment types. The one treatment type, we catch this dot, take it to 10. So 10 people have been treated by 1, and then by 2, the 10, we have to say 10 people have to be treated by 2. So we take it up to 20. And for example, 10 people have to be treated by treatment 3. Now we generate a random number in the C column, and we say is equal to RAND, rand. We open a bracket and we close a bracket, we place a star, and then we say up to 30. So this generates a number up to 30. We copy this and we continue it up to 30, and we say Control V. So many random numbers are generated. Now we take these 2 columns, go to data, and we sort it or sorted by column C. Sorted by column C. And when we say OK, you see that the first person will get second treatment and second will get first. So this is the random allocation. And if we do it over a sufficient sample size, then all known and unknown confounders between the treatment groups would be adjusted, and the only explanation of the difference in result that we see will be the treatment type. So this is the best method of controlling confounding, and that is why randomized controlled trials are the best ways to find out whether one treatment is superior over the other or not.